Testing. This is Professor Thomas with a live video, a live broadcast of going over finding the relative minimum, relative maximum, section 2.2, using the second derivatives um, to actually locate maximum and minimum values, and also sketching functions. Um, however, um, this particular section we actually use our technology to graph a lot of these functions. So for problems where it says use your technology to find the graph, or where it says graph, use your technology to actually graph it. Okay. But before we get into finding the maximum and the minimums, let's review what it means to be concave up and concave down. Notice that concave up and concave down does not mean a minimum or a maximum. It simply means that there exists in the original graph of f, there exists this curvature happening where the rate of change is not constant, the rate of change is increasing, which is f prime is increasing, like the slope is getting bigger and bigger. So we're actually analyzing the rate of change at every point. And as you can see, the slope is increasing from left to right, and so therefore we say that the graph is concaved up. Whereas here, uh, the function is concave down along this interval wherever the f prime is decreasing. And we also call this where it's less than 0, where f prime is negative. So wherever f prime is negative, it is concave down. Wherever f prime increases, it is a concaved up. And so this is part of 2.1, the first derivative test. However, there could be, in addition to the local min and the local max, there can also be some concaved behavior inside the domain of a function. And so concaved up simply means that it's kind of a convex shape, point like a U shape, and concave down is basically it is decreasing, the function is decreasing. Now clearly when you have a minimum and a maximum, those things will definitely happen, and I can kind of uh, make a quick reference to this. Let me get my pen. Hopefully this is working pretty clear. And I'll click on the pen. Now, let me get this going. Hopefully this will come out clear. Sometimes it's not calibrated, but let's say we have, this is a rough sketch of a function. Now, clearly, it's going to be decreasing along this interval. Okay, the slope, that the rate of change at every point, the instantaneous rate of change, is going from a very high to very low. Okay, and so it is definitely concave down, but it's not just concave down along this interval. It actually, if our function continues in this direction, this would also be considered the relative maximum, because right at that point f prime is 0. The derivative right there at that point is actually flat, but it still continues in a decreasing manner. Now the slope changes from positive to negative right at that vertex point. So yeah, you can have, and I'll give another example of this. It's possible where we have a local maximum and there's some other things going on. This looks like a local minimum. However, this piece, it is decreasing, but it's not a relative extrema. And so the point where it switches from increase to decrease is called an inflection point. The rate of change switches direction at that point. So, which we call the second derivative to keep track of it. If we're looking at the rate of change, which is the first derivative, well, it switches at that point. It can only switch when the second derivative is either 0 or undefined at that point. And so this is approximately where, there's probably another point of inflection as well. Another point of inflection where the point at which the graph switches from being concaved up to concave down. Right at that point, there is an inflection point, we call it. And that has to do with the second derivative test, okay? But right now, we're only concerned with what's going on at that point. So this is a test for concavity, and it's gonna we're gonna use this concept for the second derivative test. This is not quite the second derivative test, but this is a test basically showing you that you can determine where a function is concaved up or concave down. So for example, if f double prime of x is greater than 0 on an interval, then the graph f is concaved up. If f double prime of x is less than 0 on an interval, which means it's negative, then the graph of f is concave down. Okay, let's keep going. And finally, this is the definition, the second derivative test. This is the theorem, but also this defines the second derivative test. All right, and it basically summarizes, it uses the theorem of a test for concavity. Basically, we have some function f that's differentiable for every x in the interval, call it AB, and that there is a critical value, c, inside AB, for which f prime of c is 0. Then, okay, so these assumptions and conditions must be met. You sometimes may need to understand the domain of a function before you can even apply this test. So if there exists some critical value such that f prime of c is 0, then we can say that either f of c is a relative minimum if f double prime of c is greater than 0. If it's positive, the second derivative is positive, then that means there is a minimum. And if f of c is relative maximum if f double prime of c is negative, it's less than 0. Okay, and this makes sense to us because we already know that it will be concave down when the rate of change is increasing, and concaved up when the rate of change is decreasing. And so this is an example of where the rate of change is decreasing, which forms a maximum. And then they say if f double prime of c is equal to 0, then just use the first derivative test. In other words, don't even use the second derivative of all. Stick with the first derivative and make your test points. Test the left and the right intervals. But keep in mind, before you can even do the first derivative test, you have to be working with an interval that's a part of the domain of the function. The original function must be defined for those points. And that was the issue that some students were having. The function was not defined within that interval. Here's an example of a problem. It says graph the function f given by f of x equals x cubed plus 3x squared minus 9x minus 13, and then find the relative extrema. Well, what you could do immediately is just graph this function. I'm going to do a quick graph of the function. Let me get this piece here. So it looks like my function is, let's bring it back up. Looks like my function is going to be y equals x cubed plus 3x squared minus 9x minus 13. There's our function. This is what it looks like. Okay, and as you can see, the function actually has a relative maximum and a relative minimum, and it is concaved up from this point to that point, and it is concave down from this point to that point. And there also appears to be a point of inflection happening where it actually switches directions and does a reversal. The rate of change is going negative, 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 and then all of a sudden it switches and starts to go positive, positive, positive. And so that's a point of reflection going on there. All right. The graph can be helpful in figuring out what to do. So now let's go back to our problem. It says find the relative extrema. First step, find the first derivative and then the second derivative. The first derivative is 3x squared plus 6x minus 9. The second derivative is 6x plus 9. Now, we use the first derivative to find all the critical values, okay? So you set the first derivative to 0 and solve for x. You solve, you get two critical values, negative 3 and 1. These are a part of the domain. Our domain of that function is all real numbers, so there are no restrictions in our domain, so the critical values are fine. Now what we're going to do, since we have the critical values, we're going to use the second derivative test and see what happens if we plug in the critical values into the second derivative test. Now, there's only two things that can happen. Basically, we get a positive or a negative value, or we get that it equals 0. If it equals 0, then you go back to the first derivative. But if it's positive or negative, then we can state clearly that there's a relative max or relative min because we plugged it into the second derivative, and by the second derivative test we can now deduce that there is a relative max or relative min. Now to find the actual point, you plug negative 3 back into the original function to get the y coordinate. So if we plug negative 3 back into the original function, you get that the ordered pair is negative 3 comma 14, and for the f function you plug 1 back into the original, you get 1 comma negative 18. And so the original point where there's a relative max and a relative min are at these 2 points respectively. This can help you actually create the graph. There's some more points to this. We didn't talk about the point of inflection and things of that sort, but we can easily put in a relative max and a relative min around these points. As far as the end behavior, there are some other techniques that we can use to make sure to sketch the graph. However, we're not doing that type of chase. We're simply sketching the graph using our technology and then answering questions about it based on what they've asked us to do. It looks like that's another type of equation. This is another example where it says find the relative extrema of the given function, g of x, and you take the first derivative and then the second derivative, and then you get your critical values from the first derivative. So let's set that first derivative to 0. Get all your critical values. You're getting 0, 1, and negative 1. The critical values, the actual coordinates of the 3 critical values are 0, 0, 1, 4, and negative 1, negative 4. The next thing you're going to do is plug these values into our second derivative. And so basically we're going to use the second derivative test, and because our critical values are part of the domain, we are going to plug it into the second derivative and see what happens. Now when we plug 0 in to the second derivative, we get that it equals 0. So that's inconclusive. We have to work with the first derivative test. In other words, we have to test a point less than 0 and greater than 0 and see within the interval and see what happens. Now let's plug 1 into the second derivative. It's a less than 0, it's negative, so we know that there's a maximum exactly at that point, a relative maximum. And then finally, if we plug the second derivative in the negative 1 in the second derivative, we're getting a positive value, and we'll say that there's a relative minimum there. So relative max at 1, relative min when x is negative 1. These are the 2 points. But what's going on at that second derivative, right? Well, if we actually did conduct the test, we would notice that there's neither a max nor min there. It looks like it's actually increasing, or it's actually decreasing, and then it at x equals 0, the slope increases. All right. So there's some things going on there, but we know that it's concaved down and then concaved up at those points. All right. So we actually call that's actually called a point of inflection. All right. And let's go over this. Here's the theorem for the point of inflection. And let's see if it, if f has a point of inflection, it must occur at a point x naught in the domain of f, where f double prime of x naught is either 0 or that f double prime of x naught does not exist. So the assumption is that in order to get an inflection point, that is a point on your graph. This particular point must exist. Now, the reason why they're using x naught is because they don't want to use c. Now, c is the critical value for f prime, but we don't want to use c, so we're calling it x naught. But c could be thought of. Sometimes c could be x naught, depending on the situation. So anyway, f double prime x naught is 0, or f double prime of x naught does not exist. That's where the points of inflection, if the point of inflection exists, it must occur at these points. So here is a test. Determine the points of inflection for the given function given by g of x equals 10x cubed minus 6x to the 5th. We will use theorem 6. Well, they want us to immediately find all the points of inflection for this function here, for this graph. And so what we're going to do is figure out if the function has a point of inflection, it must occur at some point where x naught is either equal to 0 or the f double prime does not exist. And so we're going to take the second derivative of the function, the first derivative there, then the second derivative, and then we're going to set the second derivative equal to 0 because we know that it will never be undefined anywhere. The domain of this function is all real numbers, so we have to set it equal to 0 and see what happens. Well, there's actually, you can set this piece to 0, 6x equals 0, and you get 0, and then this piece set to 0. And when you solve this piece, you're going to get x squared equals 1/2, and then you take the square root of 1/2. So x is equal to plus or minus the square root of 1/2, which is equal to square root of 2 over 2 if you rationalize it. Okay? I know that was kind of a lot, but let's do a quick little breakdown of what that just meant. Move over the 2x and then divide both sides. And so we're getting, and I'll flip this over. So if you take the square root of both sides, you're getting that x is equal to plus or minus the square root of 1/2, which is the square root of 1 over the square root of 2. And I'm going to rationalize that. The square root of 1 is 1, and times root 2 is just root 2. And then root 2 times root 2 is root 4, which is just 2. And so we know that x is therefore plus or minus root 2 over 2. Now, if there are inflection points they must occur at x equals plus or minus root 2 over 2 or comma 0, according to that theorem. And now the reason why they got there was because they actually already knew what the graph looked like, and they can say for certainty based on the graph that these points are true. There are other tests that probably would have to be run to determine if there's a relative max or relative min, but we've already covered it here and here. And so here we have a point of inflection, and then they're also changing directions at this point and right at this point. And those are all the tools you need to graph this without technology. So just a quick little summary of strategies for sketching graphs, and it has to do with the second derivative and the tests for inflection points. First thing is understanding that you need to find the derivative, the first and second derivative, and also keep in mind the domain of your f. So when you're doing functions that have radicals in it, it has a very restricted domain. So once you know what your domain is, when it comes to testing points, be sure not to test a point. You're going to be wasting your time if you're testing points outside of the domain, because the original function, there is no graph there. The function does not exist. It has no values for those x values. It does not cover the entire plane. Let's take a look at, let's see, a few exercises from the text. And it looks like we've already kind of covered this. Even based on the graph, we know what the graph is going to look like. It's up 5 and then it's going to be going downward. So basically the graph of this type of function is something like this, where if we go up to 5 and back down, and there it is. It's kind of a little crappy picture. But what we'll do is go through the steps. So it says find all relative extrema and classify each as a max or a min. And first of all, let's note the domain of f. The domain is all real numbers. For all polynomials or quadratics, they're always all real numbers. There are no restrictions whenever we have a polynomial type of function like this. The domain is restricted when we have rationals, usually, and it's also restricted when we have square roots. But for functions that are polynomials, the domain is all real numbers, and that's going to be key to know that. So the first thing we're going to have to do is first find f prime. It's just going to be negative 6x. And now what we're going to do is find all the critical values. So we're going to let negative 6x equals 0 and solve. So the critical value is right at 0. Now, what happens if we were to take f double prime of x? The derivative of negative 6x is just negative. No matter what value we put in here, we could put in 0. It's going to be negative, which means there's a maximum. Or it means that it's concave down, which means, yeah, there is a maximum and it's concave down. It's going to be negative 6 no matter what value you put in. And so we say that it is less than 0. And so we can say there's a relative max at 0 comma what? Well, to figure out the actual point, you have to plug it into your original function, and once you do, you get 5, because when you plug 0 into the x squared, you're getting 0. So at 0 comma 5, there's a relative max. And so we come back over here in our work and we say, hey, select the correct choice below. The relative maximum are, and there are no relative minimum. So I'm going to say that the relative maximum is at 0 comma 5. This is the same type of problem. The functions are real numbers. So when you take the first derivative, take the second derivative, you get critical values. They're going to be a part of your domain. So I would definitely go to the first and second derivative tests. Same deal here. First and derivative, the first and second derivative test. This will probably be a good idea to look at. So let's actually, I'm going to pull up another map there. And let's look at this function. So we have so the first thing I'm going to do is take f prime of x. And then I'm going to locate all of my critical values. So I'm going to set this equal to 0. Now I'm actually, I like to have my x's on the left and right. So I'm going to switch it and then flip it and get that 24x squared is equal to just positive 6. And divide both sides. I'm getting x squared is equal to 1/4. Now, when I take the square root of this, the square root of both sides, I'm getting that x is going to be equal to plus or minus 1/2. The square root of 1/4 is 1/2. So my two critical values are plus or minus 1/2. Now the question is there a max and min at those values? Well, one way to test is to use the second derivative test. Plug plus or minus 1/2 into the second derivative. Well, we don't even know the second derivative yet, so we got to find the second derivative and see what happens. If I take the derivative of the first one and use the power rule, I'm getting 48x minus 0. Now I'm going to plug positive 1/2 in there. At positive 1/2, I'm going to have another positive number. So it's actually, I'm going to say that it's greater than 0. So we know that there is a minimum. We call it a relative min. And now what happens if I plug f double prime of negative 1/2 into the original function? I'm going to end up with less than 0. And so we're going to say that there's a relative max. Now the question is what are the actual coordinates of the relative min and the relative max? Where exactly are they? And so in order to answer that question, I have to plug 1/2 into the original function. Okay. Now when you cube 1/2, you're getting 1/8. 1/8 goes away. Let's actually work that out. 1/2 cubed. I'm plugging in positive 1/2 first. And there's ways to do this on your calculator as well. You're getting 1/2 cubed is 8, 1/8, and then multiply by 8 is 1, minus half of 6 is minus 3, and then plus 8. And that's negative 2 plus 8 is 6. I need the actual value. Okay. So at positive 1/2, I have 6. This is relative extrema. Now what happens if I plug negative 1/2 in there? Well, negative 1/2 is going to make negative 1/8. And so that becomes negative 1 because the 8 times a negative 8, negative 1/8 becomes negative 1. And I'm going to plug a negative 1/2 in there. So 6 times that negative 1/2 is negative 3 minus that. And so it's going to be plus 3 and then plus 8. And negative 1 plus 3 is 2 plus 8 is 10. And so my second point occurs at negative 1/2 and 10. All right, and we're going to plug those values in. Identify all of the relative minima. Well, um, I've actually identified the relative min and the relative max. So I'm, I'm, I just want to identify all the relative mins, right? So there's actually a relative min at 1/2 and 6. So and then the relative max occurs there. Okay, so we're going to do one more problem and then we'll take a break. You should always study in um, in increments of 25 to 30 minutes. It's not healthy for people to retain a bunch of information and healthy to study when you're studying more than 30 minutes without taking any breaks. And so what we'll do is we'll do this problem, we'll give it a shot, and then we'll see what happens. Now, this function seems really interesting. It's f of x equals x root 4 minus x squared. We need to know what the domain of this function is. And clearly, the domain is restricted because these values here can never be negative. So the moment we plug in a value greater than 4 per se, like 5 or negative 5, those values will not be a part of the domain. And so the directions say to sketch the graph of the following function. And then it also says list the coordinates of where the extremum and points of inflection occur. State where the function is increasing and decreasing as well as where it is concave up and concave down. So this is a complete problem and probably a little time consuming. So our first step is to take it in stride. We realize, hey, this is a tough problem. Let's graph it first and get an idea of what kind of function we're dealing with. So my function is x root, and let's double check that. I think we have 4 minus x squared. All right. Well, looks like I actually have a function and we need to know some things about it. Is there a relative max, relative min? Yeah, not only is it relative max or min, it's an absolute min and an absolute max. In other words, yes, it is concaved up and down there. Also, this is a point of inflection. It appears that right at x equals 0, there's a point of inflection happening right there. We cannot test points outside of -2 and greater than 2 that are not a part of the domain. So the domain and range of this function is within -2 to 2 and also from -2 to 2 is our domain and range. So everything is happening within a -2 by 2 rectangle so our domain is pretty pretty restricted. Um, let's see if we can answer the first question there. What are the coordinates of the relative extrema? Select the correct choice below, and if necessary, fill in the answer box to complete your choice. The coordinates of the relative extrema would be -2, and then when x is √2, -√2, and -2. And again, 1.41, that's √2 and 2. I'll put in the negative one first. And then we have √2, comma, +2. What are the coordinates of the inflection points? Select the correct choices below, and if necessary, fill in the answer box. Well, there's definitely going to be an inflection point, and let's go back to the graph again. I believe there's only going to be one inflection point. It should be right there at f at 0, 0. And as you can see, our function is increasing along this interval, and once it hits this point, it actually stops increasing. It almost stays constant for a little bit, but it actually stops increasing, and then it goes back the other way and starts decreasing. And when it does that, and there is no relative min or max there, we call that a point of inflection. So we're going to go back into our problem there and plug that value in. And now the question is, on what intervals is f increasing or decreasing? Well, the function appears to be increasing. Well, there's a lot to say. Look, now f is increasing when you're going from left to right. The values increase from left to right, like as it's going up a hill. So it's increasing from -√2 to +√2. It's increasing, but it's also decreasing from it's decreasing from -2 to √2, and also from +√2 to 2. That's where it's decreasing at along those two intervals. That looks like choice B. And these are intervals. These are not ordered pairs. I know it's a little ambiguous, this notation, but yeah, that's what we have there. On what intervals is f concaved up or concave down? We go back to our graph here, and we see it is concaved up from -2 to 0, concave down from 0 to 2. That's the best choice that I'm going to stick with. And finally, choose the correct graph. Actually, like D, it looked like the one that we were working with, and there you have it. That was it. Now, a note about doing that problem without actually having the graph. Um, you would simply have to take the first and second derivatives. You take the first derivative, find all the critical values, but keep in mind you must test points within the domain from -2 to 2, because that's the domain of, so who cares about what you get? You have to test points within the domain. Um, you can't test points outside of the domain because the function just does not exist from -2 to 2. So find all your critical values. They will be about 3 of them: 0, -√2, and +√2, and then you plug those in and into the second derivative, and you will get your relative max, relative min. You'll know where it's increasing, where it's decreasing. This is the second derivative test. This lets you know where it's concaved up, concave down. So you can do this problem. Just keep in mind that the domain of this function is restricted to -2 to +2. You can only plug in those x values into function to get a y an output, and so only all the x is ranged from -2 to 2. So at this point we'll take a break. We'll probably come back and do some more derivatives, actually solve this problem by hand without the use of technology, or a problem similar to it. We'll probably look at a radical one that has maybe to the 2/3 power or something like that. I think that'd be good to see. But keep in mind, you have to keep track of the domain. And one way to find the domain of the function is restrict this. Basically, a quick reminder on how to find the domain of a radical. Remember, this is a product, so the domain of x is all reals. So it's only going to be restricted when we look at this function. And so the domain of f, it really relies on what's the domain of this radical 4 minus x squared. And what you do is you take what's underneath the radical, 4 minus x squared, and this must be greater than or equal to 0. And this is going to let us know all the x values that makes this equation true. Now if I just move my x squared over, I get 4 is greater than or equal to x squared, and then take the square root of both sides, and I'm getting actually going to get two is greater than x, and also well, yeah, so okay, when you take the square root of 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 a variable, there's actually two values. So in actuality, before you move it over, it's x plus or minus x is greater than or equal to 2. But when you move over that negative, you're going to have two answers. So one of the answers is x is less than 2, and then the other answer is going to be switch the sign and move the negative sign over. And basically what this is saying is we're having these are all of the values a part of the domain, and anything outside of this region is not a part of the domain. These are all the values for which my function is defined for, and we're going to work inside of there. Now at -2 and 2, that doesn't concern us. The function isn't even considered differentiable at the endpoints of the graph. When we take derivatives, we have to have an interval, and everywhere along that interval the function is defined and it's differentiable and it's continuous. There's limits from both from the left and right, so on and so forth. And so if we just keep it simple and understand what we're doing, we will have much success moving forward. So this is it for now. I'm going to stop this video. If you have any questions or comments, please reach out to me.